Now, what I will do now, I apologize, this is exciting, but what I need to do before we really appreciate the excitement, I need to finish what we started last time. And I need to finish telling you about how we think about stability and instability of solutions of then laws, dynamical equations. In this case, differential, but I already told you if you use Poincare maps, there could be iterations in time. So laws can come in different shapes. Now, deterministic laws have a property that every initial condition has unique solution. So all the possible solutions, they organize themselves on lines in state space, which are called trajectories. So I will go back and discuss stability for a bit. And so because, every time you learn a new thing, it's a bit confusing. One thing that's very confusing about how people tend to write these equations, X, Y, and Z remind you of Descartes and Euclidean coordinates. Here in 3 dimensions, there's coordinate X and coordinate Y and coordinate Z. These things are abstract and they have nothing to do with coordinates X, Y, and Z, our Euclidean 3-dimensional world. These are things that I would call fields. So when you started with the example of fluid moving, it meant that you had some volume and fluid was moving on this volume. The way you think about it is that you have some state and you need, for fluid, infinitely many numbers. And if you put it on computer, 1 million numbers to tell you what the state is. And that's a complete specification of instantaneous state of a fluid. Now, what's going to happen next? That's what equations of motions are for. So at every point in the fluid, there's a little arrow, which Strogatz call F, and I call V for velocity, but it's an abstract arrow. And your equation says, your first order differential equation says that in small step in time, you will move in that direction by small distance proportional to the length of that vector. So that's a field. You think of it, there's a hillside and the grass is growing in it, the little blades, and that's why Germans gave it the name Feld, meaning field. They visualize it like that. But this is an abstract notion because your hill might be in 3 dimensions, but in physics, chemistry, etc., these states are described in thousands dimensions, million dimensions. In particular, when you go to these Fourier spaces, there are zillion dimensions that describe the field. Now the coefficient of a Fourier component is called the field associated with that direction in your basis set. So these are fields. These are not coordinates X, Y, and Z. What we want to know about these fields is when we integrate them, we learn how to integrate them. We are very good in integrating at least low dimensional ones for short times. We want to know, how good is our integration, which means if we have an uncertainty in specifying our state and uncertainty in specifying our equations, and then error due to approximate integration method like Runge-Kutta 5th order or whatever you like to use. We need to know how good this is, and that's called stability. That just says, how close or far away are the neighbors to my idealized state of the system, and where do they land with time? So that's stability in time. And I want to emphasize what I did in last lecture one more time. All of you know that there is a difference between x and e to the x. There is a difference between a number and exponential of the number. If you take the logarithm, then there's a difference between logarithm of the number and the number. The big confusion in this kind of textbooks like Strogatz is that it's first easier to study equilibria of differential equations. The easiest possible thing is to say I have something that's not moving. Velocity field in instantaneous differential equation is not moving, and I want to know what its neighborhood does. So the idea is that, if I have some equations, like x dot is v dot, and the law doesn't change from today to tomorrow, I don't have variable rates or whatever, a force outside is called autonomous system. This is like celestial mechanics. Then the neighbor, my point, this is neighboring point, the distance to the neighbor, which is d-dimensional vector in maybe 100,000 dimensions or 3 dimensions, can be estimated by looking at the deterministic equation, expanding it to the first order. So for zero term is just original velocity, and the first order is a bunch of derivatives called velocity gradients. And there are other terms, but in linear approximation, we drop them. The main object here is, if you know velocity of the field defined every place, so this is a vector field, that's some set of functions, so you know how to take their derivatives. They depend on d dimensions, so the d partial derivatives. And this object I call stability matrix, or matrix of velocity gradients. And that tells me how instantaneously the neighborhood gets sheared. And the way calculations work is that I first solve this equation for initial condition that gives me a trajectory. On that trajectory, I can compute this matrix of velocity gradients because it depends on the point. It's like the velocity, but because there is a derivative, it has 2 indices, so it's a matrix or a tensor or whatever you want to call it. And then, that thing, because it's linear approximation, satisfies differential equations, but it's not the simplest one because this varies along the trajectory. If this was a constant matrix, you could just write the exponential solution. So that's instantaneous local stability. Now, when you look at dynamical systems, what you actually need to know is not what happens at an instant of time. This is unintelligible to you, as is the equation of motion itself. You want to know what's the consequence of having instability, 5 minutes, 5 years, 1 millennium later. In other words, first thing that your theory is supposed to do is it's supposed to predict where you'll be at time t. This is done by integrating the velocity, adding it to initial condition. And the result is called the map. It says whenever I have initial condition and I integrate this velocity, I get a result. So it's a function of initial condition and integration time that gives me where I'm on trajectory. It maps me to that point. It's a long way in space. It's way away from this infinitesimal neighborhood that Newton gave us. And you really care about to know, when some time has passed, where are my neighbors? Do the same thing. So that's his map. This is not a velocity, it's a map. You expand it to first order. Now, this map has the same dimension. I started with x, I start 0, some vector in 7 dimensions. And sometime later, I'm still in the same space, I'm just in a different location. So it's still 7-dimensional vector of same units of inches or feet or whatever you're measuring various coordinates with. So when you look at this matrix, I'm comparing x at time t to x at time 0. And you can think of this, I'm changing my local coordinates. If I'm sitting on this trajectory, like General in Dr. Strangelove sitting on a nuclear bomb going to Russia on a rocket, then locally my coordinates are changing. And I want to know, I want to compare my local coordinates mt to the initial one. That's called Jacobian matrix. That's what Jacobi, German mathematician, discovered. It's a D by D matrix. It's dimensionless because I'm, comparing feet to feet. I'm not comparing feet to time or something, which was true of that local guy. And that's the important object. And it's been called Jacobian matrix since after Jacobi didn't call it, but everybody who referred to him later called it that. So there are two kinds of objects. What happens at small instant in time, that's a local shear of your neighborhood, but you really care about what happens after finite time because you want to know whether your neighbors are still busy or they run away, and etc. So that's the object that you want. Now that object you don't have, you have velocity, but you have to get that object. So how do you get it? So there are various smart ways to do it. So let me again tell you what Jacobian matrix is. So the strategy of all dynamical systems, which I now personally believe is inadequate, so my own version is very different from what I'm teaching you, but the way we learned it through about 50 years of physicists learning about it was that if I'm, for example, in 2 dimensions, I start at x0, y0. Then I have to find out how my little neighborhood changes. This notation means I take small amounts of change in x0 and y0. I want to compare it to x and y later. And one notation in your textbook is that in the process, you're looking at the ratio of partials. And if this looks mysterious, then you write it out explicitly and say, well, I want to see how the final x depended on initial x0. How did final x depend on initial y0? If I'm only in 2 dimensions, it's easy still to write this. How did the initial final y0 depend on initial x0? How did it depend on the y0? So that's Jacobian matrix written out at least in 2 dimensions. And it looks like this in all dimensions. It's not a big deal. Now, what does it really mean? Is suppose I have a law that tells me that the initial point at x, now vector space or arbitrary dimension, let's say 3 dimension, x0. As time goes by, there is a map at every instant of time that tells me where I ended up if I started here. And the way I compute this is I'm using this velocity, and I'm integrating. So this is, let's say, 3-dimensional integral vector, and if I add little pieces of it, multiplying by a small number, I'll end up moving on a curve, 1-dimensional curve in 3 dimensions. That's what its trajectory is. At every point, I'll look at it. And at time t, the vector field is something, and it really, the important thing is that I'm at point x at time t at some point in state space, and that's what this means. That point doesn't change with time. And now I started out with velocity at initial time. I integrate a little steps, I end up here. So that's the first thing, but now we are asked to say, well, if I had a little neighborhood of size dx, dy, so in 3 dimensions, I can still draw this rather nicely. So imagine there is a little bit of flat spaced little patch that's one dimension less than the space, let's say. But if you want to, I can make it the volume, neighboring volume. And now you can compute where every one of these points, in linear approximation, it's enough to compute where the corners end up. So you can compute where these neighboring trajectories go. Because system is nonlinear, they're slightly different. So the shape that you get is slightly different. So if this was a square, there'll be some kind of parallelepiped squeezed and squashed here. And now that's the meaning of this Jacobian matrix. What it does is it takes this space specified by, dx, dy, these guys, which are little vectors, all of them, right? And then multiplies them by a matrix. It depends where I started, x0. And this whole neighborhood gets mapped into a deformed neighborhood. And that's the meaning of Jacobian. Now, we know lots about matrices. We know that matrices can have eigenvalues and eigenvectors. So once you compute this matrix, it's natural to use as coordinates its eigenvectors. These are natural coordinates for matrices. So you might choose different coordinate here and there. And then what happens along the eigenvectors, you have very simple one-dimensional motion that along eigendirection, you either get stretched or squashed by the eigenvalue of this matrix, which is called a multiplier. And that multiplier squashes you if you attract in direction, expands in that direction. So we know lots about how this looks like. And now the question is, fine, but how do I compute this stupid matrix? That's easy to tell you. And you have to understand that what I will tell you is misleading, because if you put it on computer, you'll discover that you're getting exponentially big and exponentially small numbers. What does it mean to be exponentially big? It means that in some little unit of time, you lose a digit. So if I go 1 second, I have 17 digits of accuracy. In exponential growth, I lose one of them in one, so I have 14, 15, and in finite time, I lose all the precision. So exponential stuff in practice is very hard to deal with, but I can write formulas. So formulas say, if I had initial neighbor, but I keep my card open so the neighbor can be chosen any place in this little local linear patch. Then what this Jacobian matrix evaluated time t later, it just multiplies it. This is a vector times that. I get the distance time t later. And I know that the derivative of a small thing at time t, that's the first thing I told you, is to linear approximation, instantaneous stability is controlled by this matrix of velocity gradients. See, this is dimension 1 over time. So this matrix has dimension 1 over time. It's not dimension. And, this is instant. But this guy is finite time, any finite time. Years, millennia, whatever. This one we have because we have a functional form of velocity. When you take derivatives, we get it. So that's a matrix with 2 indices, but we have it. This one we won't. So let's get the equation for this one. So what we do is, let's find out how does this distance change instantaneously. I take a time derivative on the left-hand side. Now on the right-hand side, this is a constant vector because that's initial point. That doesn't change. I started where I started, and that's what it is. So this derivative only works on the matrix. So this is, matrix has d by d or d square entries. Each one of them is a function of time, where I ended up. So this is a bunch of derivatives of those functions. But I know that at any time, this left-hand side can be related to the matrix velocity gradients, but it just has to be evaluated at that time. But I know that this guy, dxt, at time t, can be related to the original one. So I write this matrix again, but now I replace deviation time t by matrix, Jacobian matrix times the initial thing, should be true for any initial condition in closed linear neighborhood. In other words, the derivative of Jacobian matrix of my trajectory at every time satisfies my local information, which I know, A, evaluate time t, multiplied by the matrix. But this is linear equation in J. And these are matrices. So what I have to do is I have to keep track of d square matrix elements. And they're controlled by a matrix of coefficients, which you know at every instant. So how do you find Jacobian finite time deformation of the neighborhood if you only know the matrix of velocity gradients? Well, you just, this is a d squared equations. And you have already written a program that says that d equations, x has d components. So you already know how to integrate d equations. But now this equation says that I have for every component, so d squared components, I have a time derivative of that component, ij, I'm not writing it, is obtained by matrix multiplication by known matrix at any time. Now I use the same program and I just add to it d squared elements. So now I have to integrate, in addition to what I have here, I also have to integrate d squared equations. So for small systems, it's possible. For Lorentz, you had 3 equations here, and now you add 9. So you have 12 equations, and any Python or Julia or whatever you're using knows how to do that. The only thing that you have to realize, this is changing along the trajectory. So it looks like trajectory is being forced. So if I'm moving on this trajectory, local stretching and squashing is changing as I go along by some, to me, unknown law, but this is actually given by matrix of velocity gradients. And you can solve these equations if you know how to find trajectories by d by 1 integrations. So now what I'm telling is a lie, but it's propagated in all the textbooks and literature. The reason why it's a lie is because, people who write formulas often don't have to do any work. They just write formulas. This is very true of mathematicians, other than applied mathematicians. And if you actually integrate this and system is unstable, you'll discover exponentials, and you'll very soon understand that you cannot have exponential increase in, let's say, student debt or exponential increase in carbon in the atmosphere or any of those things, you cannot have them. You always hit the wall. You hit the wall in a year or maybe a year and 1 month, but you always hit the wall where you cannot control it, because you find out that numbers in your computer either run out of all significant digits or they all go to zeros and you have lost all the information. So that's the truth. And to do this, you have to take a more serious course in dynamical systems. There's some nice, interesting way to think about this anyhow. So you have a Jacobian, it's a matrix at any given time. So you know this thing in principle. You know that matrices generically have eigenvectors. So this is an eigenvector. And they have generically d of them. So in d dimension, this runs from 1, 2, 3 to a number of dimensions. And eigenvectors are these special directions, magical directions for matrices in which the action of this thing, no matter where it's million times million or 3 times 3, becomes one-dimensional. You find out that all that happens is that the entire matrix gets replaced by one number called stability in dynamical systems. Usually eigenvalue, but here it's interpreted as stability multiplier. Multiplier because it multiplies the vector and tells you what the distance is along this direction. Now, whenever you have things like that, it's natural. You have a continuous time here. So it's natural to define this multiplier to take it logarithm. So define lambda to, in kth direction times time. And why do you do this? Your intuition comes from interest rates. If you have very short times, then exponentials describe how things grow. So this is a growth rate or shrinkage rate. And that's a number that you can prove in many dynamical systems has a limit while this matrix is changing in time. This multiplier is a function of time because, matrix is in time. This logarithm actually might be good. So you find out that what you really want to do is you don't want to look at stability multipliers, but stability exponents or rates of growth. Now you know that this is a real matrix typically, so these eigenvalues can be real or complex. So you know that in general, this thing up here has a real part, because if you take a logarithm of a complex number, you'll have a real part. This is a logarithm divided by time, so it's a rate in units of time. And it has a phase which tells you whether you spiral in or out as you move in time. And whether it's in or out depends on this real part, which tells you whether you're shrinking your distance to your reference trajectory or you're going away from it. For every time, everybody changes here, but for every time you have eigenvectors and eigenvalues. So you have this idea that there's an intrinsic frame, what I call co-moving frame, that if you sit on it, your eigenvectors will change and move around you and the eigenvalues will move. But if you have a periodic orbit, they will have to come back and realign themselves exactly, because initial and final point have exactly the same eigenvectors and multipliers if I'm on a periodic orbit. So there'll be a very nice way of just moving with this thing and understanding how neighborhoods move. So the first order intuition about stability is that it's described by finite time Jacobian, invented by Jacobi, who studied differential equations. And that has the distinct multipliers. They all depend where you started with and what time you had. And there are the different intrinsic vectors which describe the natural coordinates for your neighborhood. And they all depend where you start and how much time has gone. And the main thing that seems to escape physicists, these things are coordinate dependent. Now, you might be a proud portrait and quite sure that your coordinates are only correct ones, but that makes it very useless for anybody else if you publish results that change depending how it chooses coordinates. So one thing we learned about science, we are supposed to give you something that's intrinsic to the problem. For example, mass of the proton, and not the way in which the proton is oriented and sitting in a lab in Geneva. That's an engineering issue, but conceptually, that's totally irrelevant. So I told you there is stability. There is a correct way of thinking about it, which is in terms of finite times Jacobians. And I told you that this is all useless because it's coordinate dependent. Then the miracle happened. Change the name of Jacobian matrix to Floquet matrix. Now, people who take courses in condensed matter physics and some other engineering subjects like material science are used to this name, but here we don't really need to know that other people use similar matrices. I just want to emphasize the difference between Jacobian matrix to Floquet matrix. So Jacobian matrix is, I start any place, I go for any time, and I look at my neighborhood. That's described by Jacobian matrix. And it's very dependent when I started, which way everything was oriented, and how I'm measuring it. Floquet matrix is magically much more invariant, and it's associated to periodic orbits. So we will find that periodic orbits are not just cute, but kind of fundamental to understanding things. One way to think of it is think of a Poincaré section, so Poincaré section S. You start at any point in Poincaré section, but there are special points, which, in this book are X stars, where you start, you go around, you do some dance, could be quite complicated. You spend some time in Minnesota or someplace, and then you come back, and you come back exactly where you started. So it's a boomerang, trajectory of a boomerang. Or a more typical situation, equally important, you start at x0, you go someplace, and you pierce this Poincaré section at time x1. Then you go someplace, and you come back. So the map from starting any place to coming back is Poincaré map, capital P for Poincaré. And it can have a property that there are points which return. And one thing, they are fixed points, Poincaré section. But in a full space, you're moving on a trajectory, so they're not equilibria generically. You might find out that if you go 2 Poincaré sections back, you find periodic points which return, both of these periodic will return after 2 return times. you can now study these maps, call it Poincaré map, but in general, it could be continuous time. So these are maps that where you start and you either go around once or you go n times, you come back. So you either have a fixed point or periodic points that already perm. And now there's this, very simple notion that's obvious, that if I've done this once, I can just keep doing it, right? Because this orbit, which I found to last 3 seconds, will be here 7 years later because it exactly repeats itself and you never go anyplace away. So there's no point of computing it 7 years later. If I compute it in 3 seconds, that's all. So I only want one traversal, and that is called prime orbit. And I only need to compute its stability once, starting on any point and going for the prime period, the shortest period it takes time that it takes me to come back. And now if I find this one, I don't have to do any more, because going around twice will just produce one more factor of this matrix. So I'll get this matrix to the power p. And if I look just at multipliers, they'll really be nice multipliers because I'll just get powers of multipliers. So there are special orbits which are periodic, and Floquet theory studies periodic orbits. So that's why, and it introduces their stability as a matrix. So that's why when we say Floquet matrix, we mean Jacobian of a periodic orbit. That's very special. It suffices to go around once and compute the eigenvalues, a set of them, and typically in d dimension, there are d of them. You know everything about the orbit. And now something I won't prove here, but it's proven in the spring course, is that these multipliers, the capital lambdas, are invariant, meaning no matter when I measure them on periodic orbit, no matter what coordinate system I use, I change my coordinates from Cartesian to polar or to cylindrical or to some general relativistic metric and God knows what, you can prove that these numbers are always the same, they're intrinsic. And that's what we are aiming for. We can agree. So for example, we are writing something and Fizev later had uncovered something else, which we suspected was a special case of our calculation. And then we were given, that paper produced list of multipliers. It actually came from collaboration between Birmingham and Kyoto, so far away from Atlanta. And we were able to identify that this set number was exactly the same, and eventually pin it down. And even though pictures look totally different of this turbulent fluid we're studying, invariant numbers, they're like Casimir operators in quantum mechanics or masses and spins of particles. That's the real content of what you have to do. So you look at the general problem, equations are written by different people with different letters and different coordinate systems, they don't look different. If they describe the same phenomenon, you go and look for things which are common to them. And one thing that's common is that if anybody finds equilibrium point, everybody else has to find it, no matter what coordinates, because that's intrinsic, that's topological property. The next topological property is that if everybody finds a recurrent motion, I go someplace, and I return exactly back. That's a topological property. It says in state space, there's a loop that's closed, and everybody who does a calculation should find that loop. So, we have to agree that our topology of the flows is the same. That was one of the insights of Poincaré. But now there's a miracle. There's a bunch of numbers which are invariant and everybody can agree on them. So that's why I'm spending some time telling you about stability, because stability is very, very deeply profound, because it enables us to identify systems and classify them. Now, if these numbers are invariant, everybody agrees on them, then the interesting physical number is to take a logarithm of their size. Remember, we could always write this thing in exponent as a real number imaginary. So if I take absolute value, there is nothing imaginary. I'm just looking at this exponent here. And now every periodic orbit will have this number, which is, I go around once, I stretch by 17, I divide this by the period, and I get intrinsic rate. And this one has a name of a Russian nobleman who was competing or learning from Poincaré at the end of 19th century, Lyapunov. And it just says that intrinsic to unstable dynamical systems are these numbers called Lyapunov expansion, and they're invariant. They, no matter how you measure them, in what coordinates, etc., you should get the same numbers. And one says under smooth conjugacies. So if I change all my coordinates by some smooth nonlinear function of coordinates, these things are invariant. If you become professionals and you deal with nonlinear systems, I hope you will be looking for this kind of signatures of invariant things, because a big problem with nonlinear dynamics is that we tend to look at infinitesimally slightly different problems. So no matter what system you're looking at and do truncation, you get some random looking, to me, set of equations. And I'll have no clue whether these equations are like something I understand or there's something new. So I beg you, go through this kind of analysis, get intrinsic things that we can all agree on that are beyond anybody's taste or discussion. They're like masses of protons, electrons, mesons. And in nonlinear dynamics, they are called exponents, multipliers, Floquet multipliers, and sometimes Lyapunov exponents. And if we can agree on those, we can do very well.